Welcome back to our last part of the stats primer videos, or the last video in the 3-video sequence. We're still talking about probability distributions in those 4 different types of functions. So I'm trying to show you a place where you would use the d underscore function, so d norm, dt, d chi-squared, d, p, q, and now we're to r. So we did a q1, which was finding the confidence factor and a confidence interval. We've did a p, which is finding a cumulative probability, and you made your own d function, okay, which is the density or the mass function. And now we get to R, which is probably the most important of the ones, or the one that you'll use the most. Okay. The R function generates samples from a distribution. I think this is really cool, and it's not something that you should sort of take advantage of, or certainly you should take advantage of the functions, but you should not think that it's simple, or what those functions are doing are simple. So being able to simulate draws from a distribution is a crucial part of stats and data science, and it is actually something that we will do a lot in data science too. And one would argue that having draws from a distribution, like numbers that behave like a distribution, is actually more powerful than having the functional form of the distribution of itself. So what I mean is, if I can generate 1,000 numbers that come from a normal distribution with mean 0 and standard deviation 1, that's better than having that functional form that you made in the last video, if you did the last your turn. Okay, so one example that I use all the time for this is, how do I generate data that comes from a linear regression model? So what does that mean? That means that linear regression is line of best fit. You can think of it very simply as line of best fit. And so the question really comes here, in that I can fit a line that we have. Of course, we'll use linear regression functions to fit a line to data, but how do I generate data that should actually be fit by a line? I don't know if hopefully that makes sense to you. How do I generate data that it looks like it is linear? That's maybe not so easy of a question. I can't just randomly generate points all over the place, because then it'll have no pattern. But how do I generate stuff that has a pattern but looks random? I can also easily generate points on a line. If my line is y equals 2x plus 3, I can just plug in a bunch of x's and it gets me a bunch of y's. But those points are actually on a line, which is not helpful here. I need randomness. So I need to push those points out away from the line. Okay, so how do I generate data that comes from a linear regression model? Well, I guess first you need the model itself, which we'll get to a little bit later on in a little bit more depth. But it is this. Now this looks a little bit scary, but think back to your regular math curriculum. Y equals mx plus b. M is beta 1 here, and b is beta naught. And then there's one more term here, which is epsilon sub I, or e sub I, which is an error term. So the linear regression model is y is equal to mx plus b, or here it's b plus mx, plus epsilon. And that epsilon is what's going to push the points away from the line to make it look random. Now the theory behind linear regression, a theory, says that epsilon, or the e, should be distributed normally with a mean of 0, standard deviation or variance of sigma squared. Okay, and so that's this. What that means for us is that e is a normal random number. or a random normal number. And so what we want is this. So I generate points on the line. Okay, so if my line is 3x plus 5, that's the sort of relationship I want to generate. I create a bunch of x's. So here from 50 to 100 by 1/2. So the sequence from 50 to 100 by 1/2 will generate 50, 50.5, 51, 51.5, 52, 52.5, 53, so on and so forth, all the way up to 100. And then y is equal to 3 times x plus 5. That generates points on the line 3x plus 5. But then I use our norm, the random normal number generator, with a mean of 0 and a standard deviation of 25, and I need to make sure I have enough of them, so length of x there, and that gets me, well, it gets me the picture that I showed you in the previous slide if I would ggplot that, okay? And now, next question, I guess, is how can I recover that line? So now I have a bunch of points that I've pushed away from the line. If I actually fit a linear model to that line, if I fit a line to the data, would it actually be able to recover that it was 3x plus 5? Or would it think it's something wildly different, 10x plus 20? If I've pushed the points too far away from the line, maybe it won't pick that relationship back up. And that's what we're going to test here. Okay. And so what did it say? It said x is the slope, intercept is the y-intercept. And so it thought that the slope was 2.95, which is awfully close to 3, so that's really good. And it thought the intercept was 6.5, which is a little bit different than 5, but it's pretty darn close. So it looks like it can recover that line, which hopefully it should. Okay, so I've got a your turn, and then I've got, well, we're almost done, but I've got 2 more your turns to go. And this is a bit of a challenge round, which means they're harder your turns, but I do want you to try to complete them. So what I want you to do is I want you to generate 10,000 draws from a chi-squared distribution. I won't ever hear you talk about distributions, but I do have a pet peeve that people often call this the chi distribution or chi-squared. It is not chi. It's not. It is Greek, not an Indian dialect language. So chi means tea, I think, generally. I don't know exactly what language, but I know that chi means tea. Okay, this is the Greek chi, not chi. So it is not chi squared, it is chi squared. Anyway, sorry, another rant. I want you to generate 10,000 draws from a chi-squared distribution with 10 degrees of freedom. I want you to make a histogram of that, of those 10,000 draws. And then I want you to overlay the actual density function in red. Okay, and so you'll get something like the bottom. So generate the draws. That's easy from our chi-square. Okay, make a histogram. That should also be fairly easy. Then overlay it. Okay, then overlay it. Now that is a little bit harder. That's a little bit different. Okay, so it's r chi-squared. Look up how to overlay a function. Okay, it's stat function. Okay, but look up exactly how you need to overlay that d chi-squared, and then make sure you use, here I say ... density. That's actually old code, and you did a ... density like thing in a previous homework, and you used after_stat density. So do the same thing here and see if you can get that histogram. Okay, the last part, the last part of the stats primer that we want to talk about is statistical inference. And so other than prediction / classification, so other than like making a line and fitting data to that and then predicting based on that, so or classifying whether or not, say, an email is spam, or classifying, well, there are many things that I can't seem to think of at the moment. Other than prediction and classification, inference is what people do with statistics. It's the sort of big bang, the big ending of a stats class. There are two types of inference in traditional introductory stats. In Stats 1, which is sort of what we assume that you have here, when that is estimation and testing. Estimation is confidence intervals. Testing is hypothesis tests. Okay. R was made for statistics, as I've said multiple times already, and so it has great support for inference. So for confidence intervals and hypothesis tests for proportions, there's a function called prop.test that does both the test and the confidence interval. And for means, it's t.test, right? Which is traditionally a t interval, a t test, and what you would call what some people call a z interval and a z test, which is not necessarily right for proportions. Okay, proportion test would be maybe better. Okay, so my last challenge round here, since all of the confidence intervals are built into the test functions, there's no such thing as a t.interval. Okay, it comes in t.test. What I want you to do is make your own function called t_interval, okay, because dots are for losers. You never use the dot, okay, always the underscore. Make a t_interval function where you input data and output, well, an interval. So you're going to input a number of points of data. So for the t interval, you're going to use means. T is about means. Z is about proportions, generally. Okay, so the data that you're actually inputting, you could think of as like if you were trying to find an interval for the height, for heights of I don't know, a certain species of monkey or something. Okay, you would input all of the data would be all of the heights that you get. Okay, and so I define everything up here, up above in the formula. X bar is the sample mean, so the mean of the sample, or the mean of your data here. So mean of data is the sample mean. S is the sample standard deviation, so the standard deviation of data. N is the sample size, so the number of observations in data, maybe length, the length of your data. And then n-1 is degrees of freedom, which is the sample size minus 1. Okay, and so look up formulas if you need to, but try to create a t-interval function. This is going to be important because you're going to do something sort of similar in the homework. Okay, so take a second. I'm going to end this video. This is actually the last slide I have for Stats Primer, but see if you can create a t-interval function that outputs an interval. So outputs the endpoints, two numbers, which are the endpoints of the interval.